now joining us is going to be Dr. Larry Roth from Agrarian Solutions, who is going to talk about enhancing dairy reproductive success when cows are challenged by mycotoxins, which is a really timely question. So, Dr. Roth, the stage is yours.
All right. Thank you. Thank you, Todd. So let's have a conversation about the interaction of mycotoxins and dairy reproductive success. In a subsequent slide, I'm going to define mycotoxins. So let's start by what do I mean by reproductive success? Getting the cow pregnant and staying pregnant. I think that reproductive success is one of the most important economic determinants on the dairy. It's not just the cost of having to repeatedly rebreed the cow, be it semen and labor costs. It's not just the cost or the value of a dairy replacement or a beef on dairy calf, but reproductive success also determines our days in milk on the farm and what our level of milk production is going to be. So let's talk some more here about mycotoxins. What are mycotoxins? Mycotoxins are toxic secondary metabolites produced by moles. Moles are wanting to grow, and they don't want anybody else to live in their neighborhood. So it's their means of competitive exclusion to protect their niche or their environment. Moles could care less about the plant that they're growing on, the animal that consumes them, or even us humans. They're simply trying to dominate the environment in which they live. So here's a little figure that kind of gets at when do mold infections occur. And it just seems that some of our modern agronomic practices, we get more molds and mycotoxins than in the past. We think about good agronomic practices start with some crop residue, organic matter being on the surface of the soil. Well, that serves as a reservoir of mold spores to inoculate the little green leaf, the coleoptile, when it first emerges from the soil. And then we get spores that blow in, and then we get weather. Might be hot and dry, might be cool and wet, or just variable. We should stop and think that anything that challenges plant health tips the balance toward the molds and gives them an opportunity to grow. Insects come along and cause damage to the plant. That reduces the vigor of the plant. And then we have harvest. Well, is the harvest on a very timely basis, or is it cool and wet? Is it stop and go due to weather or mechanical breakdowns? All of these situations give an opportunities for mold to grow. But it's not just the mold count that leads to mycotoxins. More importantly, it's stresses that occur to the molds. With some molds, it's going to be hot, dry, such as to the fusarium and aspergillus that's going to produce aflatoxin. It could be cool, wet conditions that lead to the production of DON and T2 and Zearalenone, or warm, humid conditions that lead to the production of Fumonisin. So I really think that it's important that we monitor growing conditions, but we have to also think about what particular stresses come at what time during the growth cycle and harvest cycle that can lead to mycotoxins being produced. Here's something that we're really starting to see, and that is the occurrence of multiple mycotoxins. And let's think of an individual mycotoxin as a stressor on the cow, as we'll talk about in a subsequent slide. So when we have multiple mycotoxins occurring, it's multiple stressors on the cow. And we just see increasing numbers of these multiple mycotoxins occurring. Here's some data that came out of the state of Michigan looking at the number of mycotoxins on dry corn samples. Wow, look at that. even up as many as 10 different mycotoxins that occur on a sample of dry corn. Let's stop for a moment and talk about what might be happening to some of this, shall I call it dirty corn? Well, if we know as the row crop producer that our corn is going to get tested for mycotoxins when we take it to the feed mill or a place for milling for human use, we're going to take it to some place that doesn't do that type of testing. And so what we see happening with some of our corn byproducts, such as distillers grains, is that these mycotoxins get concentrated by a factor of 3. The mycotoxins aren't destroyed during the processing to create the byproducts. They're just concentrated. So let's keep in mind, what are the conditions in our area for the crops that we're producing? What are the conditions in areas where byproducts may be coming from? And we always need to be doing some testing. I'm a big advocate for testing. I like to see dairies sample on a monthly basis, sample their fermented feeds, be it corn silage, high moisture corn. If they're feeding their own corn, maybe testing that as well. But where we're most likely to pick up mycotoxins is going to be in the TMR. That's where we have mycotoxins coming from byproducts that we're feeding, as well as our own feeds. I also encourage folks to look at sampling their feeds at harvest, going into the corn silage bunker, going into the bin, so that we know what our inventory is. If I've got a 30,000 ton bunker of corn silage and I was sampling it going into storage and fermentation, I'm going to have an idea about the nutrient quality. I'm also going to have an idea about the mycotoxin level. Mycotoxins are not destroyed during the fermentation process, and during a poor, prolonged fermentation with plenty of oxygen available, we will actually see the mycotoxin levels go up. So test and then test some more so that we know what we have for levels. And here's the main mycotoxins that we are dealing with in North America. Aflatoxin. We typically don't see that much aflatoxin anymore because the corn breeders have done a very good job of breeding corn that is relatively drought tolerant. But we'll see aflatoxin if we're feeding a lot of cotton products or peanut products coming out of the South. And I think of aflatoxin as the mycotoxin that attacks the liver. Think of the liver as the body's biochemical factory. And if our biochemical factory is under attack, all kinds of bad things are going to happen. Milk is regularly sampled for aflatoxin because it is a class 1 carcinogen. How about DON? We see tremendous levels of DON here in North America. And I think of DON as the disruptor. It disrupts the microbial balance in the rumen and in the hind gut. It is a drain on nutrients, as we'll see here in just a moment, and interferes with gut integrity. Then we have Zearalenone. I call Zearalenone the imposter mycotoxin because it mimics Zearalenone. It ties up some of the estrogen receptors. So some folks will call Zearalenone the reproductive mycotoxin, and yeah, it does interfere with reproduction, but so do the others, as we're going to be talking about in the rest of our presentation. And then we have T2 and H2. I call them the assassin. They are perhaps the most deadly of the mycotoxins, not quite as common as some of the others, but they like to go after the high turnover cells, such as those that line the digestive tract. So we have reduced gut integrity. We see more incidents of bloody diarrhea. And if we have damage occurring to the digestive tract lining, we're more likely to get pathogens and other mycotoxins into the body and migrating to the liver. And the liver is going to be trying to detoxify those compounds, and that interferes with some of the nutrient processing. And then we have Fumonisin. Interestingly, we're seeing higher levels of this mycotoxin in recent years, and I call it the saboteur because it comes in and tries to really damage the liver, tries to damage the small intestine. So it maybe sets up the body to be more easily attacked by some of the other mycotoxins. So we need to be thinking about what are the mycotoxins that we're dealing with and how many of them and how do they come together. Hey, let's talk about digestive tract integrity. As a nutritionist, I think that the digestive tract is the most important part of the animal. Feed a great diet and then set up the digestive tract to make use of those nutrients and absorb them. On the right hand here, you see an electron micrograph of the small intestine villi. That could be the villi for a young calf, for a mature cow, or even for us. We have all these finger-like projections to increase the absorption of nutrients, but the cells lining those villi serve as kind of a castle wall. Their objective is to protect the body. See, you take one drop of fluid from the digestive tract, and there's more bacteria in that little drop than there are people on the face of the earth. And there's a constant battle between the good organisms and the bad organisms. And so the small intestine lining has an important job to keep the pathogens in the digestive tract. They're also responsible for keeping the mycotoxins in the tract. But it's these cells that absorb mycotoxins. And mycotoxins are going to seek to kill these cells. And then we get heat stress. We get other conditions that lead to leaky gut. Let's look at this in maybe a little bit different way with this little drawing down here. We go from the left where we have normal lining of the tract. We have our villi or epithelial cells, and then note the junctions between the cells. Those are supposed to be called tight junctions because they're tight. But if the animal becomes dehydrated, we have shrinkage of the intestinal lining cells, and the tight junctions no longer are tight. They become a disrupted junction. And what had been a barrier, think of it as mortar between our castle blocks in the castle wall, and now becomes open and becomes an interstate highway for pathogens, mycotoxins, and other bad stuff to get into the body. So we got to be thinking about how do we protect our tight junctions? And there's ways that we can do that. Things with phytogenics, things with hydration. And then we have this transcellular. That is where bacteria, viruses, mycotoxins actually cause death of the intestinal lining cells. And that block of the castle wall is now gone. And it's that much easier for bad stuff to get into the body. So here's where the battle takes place for liver health. Here's where the battle takes place for protecting the immune system. If we lose this battle at the digestive tract lining, now there's nutrients required to repair the gut lining. There's nutrients required to repair the liver, which is going to be under attack from mycotoxins and pathogens. And those nutrients are going to be diverted from more productive uses. And then we need to think about the immune system. I think of the animal's immune system or our immune system as being the military that defends the body against invading agents. Well, this military requires glucose. And we need glucose for a variety of uses, as we'll talk about. And the immune system also uses nutrients, also requires antioxidants. So the more we lose control of the digestive tract lining, the more reallocation we have of nutrients, the more nutrients that are required to supporting the immune system. What could be wrong with that type of picture? Well, let's look at it here. This slide is looking at nutrient allocation in the dairy cow. Just as we budget our finances and our time, the cow budgets or allocates its nutrients. And so on the left here, we see when things are good, there's nutrients that goes for maintenance, for milk production, reproduction, and defense. But whenever we have metabolic challenges, this could be acidosis, could be ketosis, could be metritis, mastitis, could be respiratory distress. Whenever we have a metabolic challenge, the body now, in an effort to stay alive, shifts more of the nutrients to simple defense, staying alive. We don't have as many nutrients for milk production. We don't have the nutrients needed for reproduction, the main topic of our conversation here today. So it's important that the animal mounts an inflammatory response whenever it is challenged. But we have to have a strong inflammatory response to resolve the insult, resolve the challenge, so that nutrients can now go back toward productive purposes. Hey, it costs nutrients to feed the cow. Those nutrients cost money. And as long as that money or nutrients are going to simple defense, we're losing out. We don't have money going to the profit-making practices of milk production or reproduction, or with some of our animals, depending on the stage of growth, to growth. Here's one of my favorite slides. This is the Britt hypothesis. And this comes from the 1992 bovine practitioners' proceedings, and it has appeared since in different forms. But basically, it's asking us to think about the follicles that are produced by the cow and when they are actually initiated, and to think about the nutrients that are required. One of the key nutrients required for follicle development is glucose. The glucose isn't used so much by the follicle as an energy source, but rather as a carbon source. The follicle is very fast growing and needs carbon to do that. So glucose is shunted away from other purposes, such as the immune system, making lactose for milk, and other purposes. The glucose is simply going over here to help with follicle growth. But if we have these other challenges taking place, now it's the immune system, it's defense, that is soaking up all the glucose. Our follicles don't develop like they should, or they're an unhealthy follicle, and reproduction suffers. So here's the Britt hypothesis, which I think has survived the test of time and is said in different ways today by many different researchers. But negative energy balance and associated changes in metabolic hormones impair follicular development. So I think so many of the reproductive challenges that we see with dairy cows today are summed up in the previous slide, showing how nutrients are reallocated, and this slide showing the tremendous demand that the follicles have for glucose. And I think that sets the basis for our challenges with mycotoxins. If mycotoxins are destroying digestive tract integrity, we've got to shuttle nutrients there. If we don't have the glucose for follicle development, because glucose is over here dealing with the mycotoxin challenges, follicle development doesn't happen. So to me, it all comes to what can we do to defend the digestive tract integrity against the mycotoxin challenges. So for a long time, nutritionists, be it ruminant or non-ruminant, have selected different feed ingredients and have said, hey, these can bind mycotoxins. Well, the Cahal et al. Research group has done a tremendous amount of research looking at these different feed ingredients, and you see classes of them, here on the left-hand side of this chart. And they took 68 different peer-reviewed studies, put them together in a meta-analysis. And this is peer-reviewed research that appeared in the Journal of Animal Science in December of 2022. Callaway et al. Has also published their research over a number of years at the dairy science and animal science meetings, but they put everything together in this nice meta-analysis for the Journal of Animal Science. So here's how this research was conducted. Take these different feed ingredients singularly by themselves, mix them in an in vitro situation with one of these mycotoxins across the top at a pH of 6.5. Kind of duplicate what's going on in the rumen. Let it mix for several hours, and then wash it, shall we say, at a pH of 2 to kind of duplicate the stomach in non-ruminants or the abomasum in ruminants. And then what percentage of the mycotoxins remain bound to these different feed ingredients? Well, you can see from this peer-reviewed research that aflatoxin can be bound by just about anything except a yeast cell wall. DON, which we see to be very common here in North America, really isn't bound by much of anything. We come over to Zearalenone, maybe our number 2 mycotoxin challenge, really not bound by anything other than charcoal. We can say much the same for Fumonisin, ochratoxin, which is more of a tropical mycotoxin, and T2. Now, so this is the bad news, that our traditional feed ingredients, which have been used to bind or protect the animal against mycotoxins, are relatively ineffective. But the really bad news that I can send to you if you send me an email, but is available in Journal of Dairy Science, is that these feed ingredients are probably more effective at tying up or binding, reducing the bioavailability of vitamin E, the amino acids lysine, methionine, and threonine, and has some effect on minerals as well. Well, shoot, those are all the types of things that we need to mount an immune response to the mycotoxins. So I guess what I'm saying is that the traditional feed ingredients that we have used to protect against mycotoxins aren't that effective against protecting against these challengers. They tie up the nutrients that the producer is paying good money for and leaving the animal exposed. So what are we going to do? Well, at Agrarian Solutions, we have a relatively unique cell wall deficient bacteria technology that we have been using for 27 years to provide mycotoxin protection to a wide range of species, non-ruminants as well as ruminants. And this is an independently conducted study that was done to evaluate the product DTX, which is the cell wall deficient bacteria technology, supplementation to early lactation cows, and looking at milk production and reproductive performance. So this was conducted at a 3,600 cow dairy in New York State that was experienced with conducting feeding trials. It was an independent group of research-minded vets that actually conducted this work. So there was a control group and a group that received this, I'm going to go ahead and call it probiotic technology. This went on for about 9 months. We sampled TMR samples on a biweekly basis, and our objective was to evaluate milk production and reproduction for the first 150 days in milk. For the sake of brevity, I'm going to say that we had an improvement in milk production, and we're going to focus today on reproductive performance. This study utilized over 920 cows that were randomly assigned at calving to either the control group, standard management and feeding practices, or to the DTX group that got the probiotic technology. And so we had first, second, and third and greater lactation cows, but over 920 cows utilized in this study. The reproduction protocol was that all cows were synchronized for service at 73 days in milk. Those cows at first service received an embryo. 90% of the first lactation cows did. 99% of the second and third lactation cows received an embryo. And so a very aggressive ET program. 100% of the fourth and greater lactation cows received conventional beef semen. Those first, second, and third lactation cows that did not receive an embryo received sexed high genetic value Holstein semen. First preg check was 28 to 34 days post-service, be it ET or AI, and then reconfirmations were at 61 to 67 days post-service. So when we look at Dawn sampled throughout the study, we see there was no statistical difference between the two groups. On a part per billion basis, we were a little bit over 1,500 parts per billion, which I think most nutritionists would call that in a high-risk category, just based upon Dawn itself. But these cows were also challenged by Zearalenone. Zearalenone did not differ between the two research groups over the course of the study and averaged 147 parts per billion. And we would consider that to be a medium risk level. So a high risk level of Dawn, a medium risk level of Zearalenone. So we got multiple mycotoxins, multiple stressors on these cows, and we have Zearalenone, the imposter mycotoxin, to tie up estrogen receptors. So let's see here what happened for reproduction. Here's a summary of all of the lactations together. And we saw the same trend in all of the lactations, but just for the sake of brevity, I've combined it all here. You can see what percentages of the cows that freshened in the two groups were bred. Some of the cows were called do not breed. So what this column here does is it follows these 407 cows that were bred, going all of the way down through the final preg check at 61 to 67 days post-service. This column here follows these 422 cows who freshened and went on to DTX right after freshening, and follows them all of the way through their final preg check, again, 61 to 67 days post-service. You can see there was no difference between the two groups for cows who were bred off of estrus, those who received embryo, and those who were bred off of a timed AI. So let's look down here at pregnancies per service. So think of this as a percentage. What percentage of the services resulted in a pregnancy here at this point, which would have been 28 to 34 days post-service. 37.7% of the services resulted in a pregnancy for the control cows, but those receiving the DTX probiotic technology was at 45%, a statistical improvement. You can see the pregnancy losses between first preg check and second preg check, but at the final preg check, again, 61 to 67 days post-service, 30.3% of the services resulted in a pregnancy for control cows, but for those supplemented the DTX probiotic technology, 36.4%, or 6.1% percentage units more pregnancies per service for those getting the DTX. And it was at the 0.06 level, that would be a strong trend. Then we come over here to breaking it out by artificial insemination versus embryo transfer. Wow. Supplementing the probiotic technology at the first preg check resulted in 7 percentage units higher. When we come back at the final preg check, if my math is right, that's going to be what, 9, or yeah, it's going to be over 10 percentage units higher pregnancies per service for the cows getting the DTX technology. So when we start thinking about what is a pregnancy worth, is it the value of that $1,500 day-old calf? Is it the value of the dairy replacement? Is it the value of not having to come back and breed the cow again and keeping our days in milk low? But that's a pretty strong economic improvement right there. And then we look at embryo transfer. Almost an 8 percentage unit improvement in pregnancy at the first preg check, and a 4.3 percentage unit improvement at the second preg check. The dairy valued some of these embryos at $2,000. So turning one of those embryos into a pregnancy is a very strong economic incentive. So how did all of this happen? If we're able to improve gut integrity, if we're able to spare nutrients from having to defend against the mycotoxins to go to more productive purposes, such as milk production, where we saw an improvement with multiple lactation cows, and go to improving reproductive success, which we saw here on the previous slide and this slide. So in our conversation today, I've tried to show that mycotoxin contamination is a major factor in dairy nutrition. When we look at common practices of minimum till, no till, high planting rates, we're seeing that molds are present. Challenges are taking place weather-wise that lead to molds producing mycotoxins and multiple mycotoxins. We've looked at an independent peer-reviewed study that shows that supplementing certain feed ingredients to bind mycotoxins has mixed results. Poor results for protection, and unfortunately does tie up some nutrients. And then we looked at how supplementing a unique probiotic technology enhanced artificial insemination pregnancy rates by 29%. And we also looked at how that same probiotic technology improved embryo transfer pregnancy rates by almost 16%. So for you to walk away with a realization, mycotoxins are an issue with ruminants. We need to have an aggressive sampling program to determine if we need to employ a mycotoxin mitigation strategy, determine if that strategy is successful or if it is reducing nutrient bioavailability. And I would contend that here is a probiotic technology that under research conditions improve reproductive success. So, hey, I appreciate your participation today. And do we have any questions that we can answer?
Well, thank you very much, Dr. Roth. So we have one question already about, can you briefly talk about how the cows, or excuse me, that was the second question, sorry. You mentioned research about the common mycotoxin binding items that binding the mycotoxins, but also binding some key nutrients. Can you restate or let us know where we can find that reference for that research?
Yeah, Cahal et al., Journal of Dairy Science 2020. They did a very nice review looking at research that they had done in their lab and others had done for some of these common feed ingredients that folks use for mycotoxin protection. And then looked at B vitamins, which may not be that important to us in the ruminant world, but are important in the non-ruminant world. And then looked at vitamin E and the amino acids, lysine, methionine, and threonine. So Journal of Dairy Science, Cahal et al., 2020, or contact me and I can send that to you.
Okay. Well, we had another question that popped up on if you would briefly talk about whether cows respond differently to mycotoxin challenges depending on lactation stage.
Perfect. Great question. How might cows respond differently to mycotoxins depending upon lactation stage? Let me expand that a little bit to include the dry period. During the dry period, so often we don't think about mycotoxins, but this is when the cow is going through determining colostrum quantity and quality. She's getting ready for the next lactation. So, what is the load put on the immune system at that point? She's also putting nutrients into the calf growing inside of her. This is the time of greatest fetal growth. So we have extra competition for nutrients at that point. So for dry cows, we have the competition for fetal growth and colostrum quantity and quality being determined. For first lactation cows, they're still growing. So there's that competition for growth for nutrients. And then as we get into our higher production cows, they have such a drive to produce milk. They're going to do whatever it takes to do that. And that's where the glucose going to lactose comes into play. We can simply say, Todd, no glucose, no lactose, no milk, because of lactose being a relatively fixed percentage in milk. So what are the challenges on the cow, and how is she going to respond to those different stressors? Oh, and then let's put heat stress on top of that. Heat stress further leading to leaky gut and all of the immune challenges that come there. So, and then let's think about our mycotoxins, more the T2 and Fumonisin affecting the liver, or is it more of the DON affecting rumen bacteria and digestive tract lining and the liver to a little bit? Or is the mycotoxin in question Zearalenone, the imposter mycotoxin, blocking the estrogen receptors? So that's how I would look at different responses to the mycotoxins depending what stage of production that we're at.
All right. Well, thank you very much, Dr. Roth. We really
Thank you.
appreciate it.